Hello everyone, welcome to a new video. Today I'm going to do some calculus. So what do we have? One sec, let me just get this sorted out. There. We have the integral from 0 to 1 of what? Sine of natural log x all over natural log x dx. That's our function for today. How do we do this? Let's call it I for now. Alright, before we embark on our journey, let us replace the numerator with an identity. So this is the identity I'll write on the side. Sine of any angle, we can call it, I'll just call it alpha. Could be imaginary, could be real. This is going to be equal to, according to the one of Euler's identities, e to the power of I alpha minus e to the negative I alpha all over 2i. So instead of alpha, if we have ln x here, that looks terrible. I'll just put a circle around it. So we have sine of ln x instead of alpha. I'll do this. This is going to equal e to the power of I ln x minus e to the negative I ln x all over 2i. Let's simplify this. So in order to simplify this, you bring the i's, let's do some stuff in our head. You bring the i's there as exponents in the logs, and then you cancel out the e's and the ln's, like this. So sine of ln x will basically just equal x to the I minus x to the negative I over 2i. If you need to pause and think about that, how I got that, then feel free to do that, but I'll just continue. So I can replace this with the numerator. Let's do that now. So the integral goes from 0 to 1, and it's the same as x to the I minus x to the negative I all over 2i. And on the denominator, we happen to have an ln x. I'll just write the ln x over here, dx. Okay, now we have this. How are we meant to do this? And did I just make our job more complicated? I didn't make our job more complicated, but it's still tough. You'll see what we do here. So I need to do a few things. Firstly, I need to re-express this in a form that is easy to integrate. To do that, I will introduce a new parameter. Function, let's call it f of, what should our new parameter, our new variable be called? I'm going to call it, I need to pick any letter, is it Greek, Latin, whatever. Let's call it, I don't know. Let's call it sigma. There we are, my favorite letter. F of sigma equals the following integral, x to the I sigma minus x to the negative I over 2i ln x dx. Now, if you notice, we have two variables within this integral, like this, and we're going to do something cool. We're not going to treat both of these variables as variables at the same time. When we're dealing with the sigma, we're going to treat it as a variable and x as a constant, and when we're integrating the x, we treat x as a variable and sigma as a constant. So that's what we call Feynman's trick, or Feynman's technique, because he was the one who popularized it, really. So if you notice, f of 1, if you sub in sigma equals 1 into this, you just get the answer. F of 1 is just the integral that we were originally trying to find. This is some vital information for later. So how do we get from f of sigma to something that we can integrate? So I'll just rewrite this all here. 2i ln x dx. Okay, so step 1, differentiate both sides in respect to sigma. So I'll write d over d sigma here, and I'll write d over d sigma there. So the left hand side, you just get f prime of sigma. I'll use the prime notation. The right hand side, this is the cool bit, the fun bit, where you take this and you bring it inside the integral. You end up with this is what we use as our notation. We use this curly d, this partial d, over partial d sigma. And we have the rest of the function, x to the I sigma minus x to the negative I over 2i ln x, and it's still an integral. How do we do this? So we need to differentiate this in respect to sigma, then integrate the answer in respect to x. And that's what f prime of sigma is. And then we integrate both sides and we get f of sigma. And then we sub some stuff in. You'll see what will happen. So when we are differentiating in terms of sigma, treat x as a constant and sigma as a variable. This is vital. Once we do that, we get f prime of sigma equals the integral, and we need to differentiate this. We treat x as a constant and sigma as a variable. How do we do that, you may be saying? Well, there's a rule. If we were to differentiate a function in the form in the form a to the power of u, where u is a variable and a is a constant, this is just a to the u ln a. Using that, if you differentiate this in respect to sigma, where sigma is a variable and x is a constant, you end up with x to the I sigma ln x multiplied by the derivative of the exponent I. There we are. And this is all over 2i ln x, right? 2i ln x and then dx. The reason why, if you're wondering, in case, what happened to this part of the function? What happened to that? Well, x we're treating as a constant, I is always a constant. This constant differentiated in terms of a variable literally just gets you 0. So 0, we don't need to write 0 over there. So now, if you look at this bottom line over here, we can do some cancellation. We can cancel this ln x with the ln x and the I with the I. And you're left with, I'll scroll down, f prime of sigma is equal to all this. I'll put 1 over 2 there. X to the I sigma dx. And now we need to integrate the function in respect to x. When we're integrating in respect to x, treat sigma as a constant and x as a variable. So this is what Feynman's trick is all about. Changing the roles of all these variables, right? So sigma in this situation is literally a dummy variable. Let's see what we can do here. This is just going to be half times, how do we integrate this? We get x to the 1 plus I sigma divided by 1 plus I sigma with the limits 1 and 0. Now we sub in 1 and 0 into this, and if we were to do that, sub in 0 into this, you just get 0, because 0 to the power of anything is almost to the power of any normal number is 0. So I'll cross out the 0, and if you sub in 1, you end up with 1 to the power of something, which is 1 over 1 plus I sigma multiplied by the half. So this implies that f prime of sigma is equal to all this. So if this is the case, we need f of sigma. To get f of sigma from f prime of sigma, we integrate both sides in respect to sigma. So we end up with this. This half over here is just a constant that's been multiplied, so we can take it to the outside like this. Let's move the equal sign a little bit to the left, like this. Okay, so on the left hand side, clearly we just have f of sigma because we're reversing the prime with the integral sign. And on the left hand side, sigma is a variable in the situation. We get half natural log of 1 plus I sigma multiplied by divided by I, plus c. How did I get this? Well, this, you can just take a substitution, let u equal the denominator. I'll just write that here. Let u equals 1 plus I sigma, du equals I d sigma, d sigma equals du over I. Sub in du over I in place of the d sigma. I'll just write the d sigma here, like this. Sub it in. You end up with a bunch of stuff cancelling, and yeah, that's how you get this natural log here. So anyway, we have this. We need to find plus c. Keep in mind from earlier that this is still equal to the following integral. So if f of sigma is equal to this integral, and it's also equal to that, and we need to find c. In order to find c, we need to find a sigma value to sub in that makes the whole integral equal to 0. That sigma value happens to be -1. So let sigma equal -1. We get f of -1 equals 1 over 2i ln 1 plus I sigma. I sigma in this case is just negative I because sigma is -1. So ln of 1 minus I plus c, which is equal to this entire integral. Now, if we sub in sigma equals -1, we end up with x to the power of negative I minus x to the negative I on the numerator, which is equal to 0. So we end up integrating 0. So if you integrate 0, you just get 0, right? So therefore, this entire thing is equal to 0. So then you can solve for c. C is going to be equal to negative 1 over 2i ln 1 minus I. So it means that f of sigma is, we just sub in the c value. F of sigma is equal to 1 over 2i ln of 1 plus I sigma minus, now we put the plus c here, like this, right? And if I were to scroll up, just as a reminder, f of 1 is the answer. F of 1 is the answer. Sub in sigma equals 1, you get the answer to the integral. Because this sigma over here is basically like having a sigma there, but that sigma is 1, right? So let's go all the way to the bottom. There we are. So if we were to sub in f of 1, if we were to sub in sigma equals 1, we get this. Natural log of 1 plus I, where sigma is 1, minus the natural minus 1 over 2i times the natural log of 1 minus I. Okay, firstly, we can factor out this. But before I continue, I'd like to say, this is the answer. We just need to simplify it. We're nearly there. We've nearly done our marathon. Why did this summon the keyboard? So this can be written as 1 over 2i times ln 1 plus I minus ln 1 minus I. And these two logs can be combined. I'll write it here. This is just ln of 1 plus I over 1 minus I, right? Because we're using the rule of log A minus log B equals log A over B, right? So that's what we have. We're working with this. We can simplify what's inside the ln. 1 plus I over 1 minus I. If I were to multiply it by 1 plus I over 1 plus I, you end up with a perfect square at the top. 1 squared plus 2 times I times 1, which is 2i, plus I squared. And on the bottom you end up with a difference of 2 squares. 1 squared minus I squared. And I can be replaced with minus 1. This is minus 1. Sorry, I squared is minus 1. There. So on the top we get 1 minus 1, which is 0, and you're left with 2i. And on the bottom you get 1 minus minus 1, which is 2. The 2's cancelled out, you're left with I. So therefore, the integral equals f of 1, which equals 1 over 2i ln I. Because all of this here, we rewrote it as this, and this happened to be I. So we have this. This is our answer, but we can go a little bit further. ln I, if you go into the complex world, this bit is just equal to pi over 2 times I. I won't bother explaining this. You'll have to do some further research. But this is then equal to 1 over 2i times pi over 2i. And these cancel. You multiply the 2's together. Pi over 4. And we are done. So just to write the answer nicely in one big line at the bottom, let's do it in the color white. Therefore, the integral from 0 to 1 of sine of ln x over ln x dx is equal to, we rewrote it as this, and that happens to be pi over 4. There you go, we are done. Thank you for listening. This is probably my favorite integral of all time, using Feynman's integration technique, and I hope you enjoy it. See you another day.